Hi, I'm Rex Black, President of RBCS. Welcome to the RBCS YouTube channel. Hey, I hope you enjoy all these free resources that are available here. And do us one favor. We need to keep the lights on and we need your help to do that. So, when you need testing and quality related services, training, consulting, expert services, you name it, let us be one of the bidders on that next job. We don't expect to get all of your business, but we'd like to get a chance. Thanks and enjoy the shows.
On behalf of RBCS, RBCS Australia, RBCS New Zealand, and Software TestWorks, we welcome everyone today to this webinar on code coverage metrics, how to use and misuse them. I am Rex Black, President of RBCS, a worldwide testing and quality assurance firm serving clients ranging from small startups to Fortune 20 global enterprises. Since 1994, RBCS has been both a pioneer and leader in quality hardware and software testing. RBCS has offices in the United States, Australia, New Zealand, and Sri Lanka with partners around the world. RBCS delivers insight and confidence to our clients, helping them get quality software and hardware products to market on time and with measurable return on investment. RBCS has a team of international consultants that deliver customized training, consulting, and outsourcing services for companies that are looking to improve their test and quality assurance practices. RBCS has helped hundreds of companies reduce development and support costs while assuring the best quality products are delivered to customers. I am the author of Pragmatic Software Testing, Advanced Software Testing Volumes 1 and 2, Foundations of Software Testing, Critical Testing Processes, and Managing the Testing Process. I hold a degree in Computer Science and Engineering from UCLA. I'm also past president of the International Software Testing Qualifications Board and the American Software Testing Qualifications Board. Before we start the presentation, a couple of housekeeping notes. If you have any questions during the course of the webinar, please feel free to submit them throughout the presentation via your webinar interface. There's no need to ask for presentation copies, as the presentation will be on the web at www.rbcs-us.com. If you are having problems with the audio or visual components of this webinar, please contact GoToWebinar support. If for whatever reason you cannot get to the webinar online, or if you are dealing with an unreliable connection, please download the slides from the basic library at www.rbcs-us.com. Be sure you use the telephone to connect, not voice over IP. And one more note before we start. The last time I did a webinar, just a couple weeks ago, it was snowing here in the Texas Hill Country, and now it's spring. So there's just no understanding the weather these days. Before we start, give me one moment, please. I want to check a technical issue here. Okay, thank you. I wanted to confirm that everybody could hear me because I was having some audio weirdness earlier. So today's presentation is on code coverage metrics. Lots of people are interested in unit testing these days, and one key to unit testing is achieving adequate code coverage. But what code coverage metrics exist, and how can we use them? And how do we make sense of what certain unit testing tools might tell us about coverage? So this presentation is designed to help you sort some of those details out. So code coverage metrics are basically tools that will allow you to measure the extent of white box test coverage. Now, when I say tools, I'm using that term loosely, not necessarily automated testing tools, though there are automated tools that do this. But They're techniques that will measure how much white box coverage you've achieved. So at an overview level, what are the types of white box coverage that can apply? Well, we're going to look at 4 groups in this presentation, 4 groups of code coverage metrics that you might run across or encounter either in the use of some sort of automated unit test tool or in your studies of the field of testing, and this should help you make sense of these. The first group will be what would be called sort of classic control flow coverage, which is statement, branch, condition, multi-condition, multi-condition decision, and loop coverage. And those are, if you read, for example, Boris Beiser's book, Software Test Techniques, you'll run into those there. Now, the next group is Mccabe's cyclomatic complexity and the basis path and basis test concepts that are put forward in that technique, and that's something that you might run into. For example, there's a paper out on the internet. I don't remember the exact URL, but if you do a Google search for structured testing Mccabe, I think would be the right keywords, you'll find this. It's an extensive PDF that describes this whole concept, how it works. Now the next group is the set use pairs, which is looking at data flow. Now the previous 2 were looking at control flows, in other words, the sequencing of statements. In set use pairs, what you look at is data flow coverage rather than control flow coverage, and you try to figure out how data is moving around in between data structures in the application and design test to cover that. And then the last is the checklist-based test requirements technique that Brian Merrick came up with, and this considers both data and control flows, as you'll see when we get to it. So we'll look at each one of these techniques. Now, we're also going to take a look at how white box testing compares to other types of testing in terms of, for example, its defect detection capabilities and what it can and can't do for you. Now, are there tools available to help with this? Yes, there are tools, and we'll talk about that a little bit towards the end of the presentation. And we'll also talk about the kind of bugs that white box testing can miss, because it's important to understand that just because you've quote-unquote covered the code does not necessarily mean that you have no bugs left and that you can have 100% confidence in your software. So, code coverage and white box testing, what can we say about those in general? Well, one thing is that we can say that these are dynamic forms of testing when you're looking at code coverage. In other words, the object under test, the system under test, has been compiled or is being interpreted by an interpreter, if that's how it works, and it is actually executing. And so that means that the item under test is executing. We are creating test conditions by submitting inputs and other types of events, and then we are actually comparing the actual versus the expected results. Of course, that's key to any form of test execution. If you're not comparing the results, then there's really not a whole lot of point to what you're doing. Now, I've looked at this a few times with a number of clients, and one of the things that we've found, if you take your system under test and you produce what's called an instrumented version of it, where you can measure the code coverage that's being achieved, and you look at the purely requirements-based set of tests, it's not unusual to see that you're actually only covering about 20% of the code, which is pretty dismal observation, I suppose you could say. but it is the case that that is often often a lot of holes in your code coverage when you use purely requirements-based type of approach. So it would be good to know what 80% of the code you're not testing so that you can figure out, is this something I need to worry about? Is this a hole that I need to fill? And that's an important aspect, even if you're not involved in doing unit testing. If you're just a system tester or acceptance tester and you say, you know, hey, why do I need to know this? How does this help me? Well, it helps you know what you're not testing with your black box tests so that you can think about what you might want to add to cover that. So basically, what we're doing when we're doing a code coverage analysis or a form of white box testing, we are designing tests based on how the system works internally. And again, this can be either via the control flows, looking at how control flows through the system, and again, control flows just refers to the sequencing of statements. We can look at data flows, which is figuring out, as I said, how the data moves through data structures. And we can also use standard checklists or bug taxonomies to guide our testing. Say, well, we're going to look for a particular kind of bug, and that's the Merrick technique that we'll look at. Now, it is possible to do code coverage analysis manually, but possible only in the literal meaning of the word possible, like there is a path to get there. Just as it is possible to traverse the entire world with a pair of boots and a kayak. If you could conceivably do that, but you might not enjoy the experience, and you might not even survive it, because it would involve walking through the code as you ran your tests and looking at what was covered and what was not. And that's going to be a very, very painful experience, very tedious and very easy to make mistakes. So typically you are going to want to use some sort of code coverage analysis tool, such as the ones that I mentioned earlier, that will instrument the code and then produce a report for you at the end of that process. And you can find both open source and commercial code coverage tools. I've seen and used both. So, excuse me. Let's look at a couple more details here. I get some water for my poor throat. So let's start with code-based control flow types of tests. And again, control flow refers to the sequencing of statements and looking at different sequences of statements that can occur. Now, the big kahuna of control flow coverage, if you will, is what's called path coverage, which would be that if you were to take the statements and number them, and if you achieved path coverage, then every possible numerical sequence of statements that could occur would have been tested at least once. Now, as a practical matter, that is impossible because generally speaking, you have an infinite number of potential paths through the code in any sort of real-world scale system. You've got a lot of loops, and you've got a lot of branches and so forth, and some of those loops have an indeterminate number of things that they can process, and in some cases the application can run indefinitely. So there really is no way to achieve path coverage. So we're going to have to scale down from that. We're going to have to say, well, what are there in the way of achievable levels of code coverage? So one of the levels of code coverage, the lowest level of code coverage, is statement coverage. Now, in statement coverage, what we're saying is we want to make sure that every executable statement in the program has been executed at least once. Now, notice I said executable statements, so I'm excluding comments and compiler directives and those sort of things. Most programming languages have non-executable statements that can occur, but every programming language that I've ever used, and I've used quite a few of them in my career, has some fundamental concept of the executable statement, which is some atomic unit of processing where you assign a value to a variable, or you perform a calculation on a variable, or you do nothing. In some cases that can be a statement, just a semicolon by itself on a line. So however the concept of a statement is defined for a language, you've achieved statement coverage when every statement, which is defined as an executable statement by the programming language, has been executed at least once by some test. And again, the practical way of doing this, you're going to have a program that's going to produce what's called an instrumented version of the code, and that will have probes inserted into the code that will keep track of where the control flows, and it'll be able to know whether you got into a particular block of statements. And if you've entered a block of statements that consists simply of executable statements, non-branching, non-looping type of statements, then you will run that entire collection of statements from beginning to end. So if you run the first one, you'll run the last one in that sequence. So if you think of a block in, for example, C, starts with a curly brace, and then there's a sequence of statements in it. And assuming that it doesn't contain any ifs or fors or switch cases or anything like that, then the last curly brace terminates the block. If you run the first statement in that block, you will run every statement in that block. So statement coverage is going to keep track of that, and if you're using a tool, you'll be looking at have these statements been covered. And many times the tools will be nice, and they'll after you've run the program, you can actually step through the code, and it will color indicate in some way in the code whether something has or hasn't been touched by the tests. So you'll be able to see that. Now in branch coverage, we're going to say, well, all right, it's good to get statement coverage, but software exists to make decisions, basically to do one thing or another. I mean, if everything could be done through a single sequence of executable statements, and anything could theoretically be done with a calculator, but in branch coverage, we're saying, well, a control is going to flow, and it's going to get to a point where there's something like an if statement or a switch case construct or something like that, and we want to make sure that every branch, every decision that can be taken has been taken each way. So for an if statement, then we have a true side and we have a false side of the if. For a switch case construct, we have the case blocks, which are the labeled blocks that the switch directs the control flow to based on the value of the switch variable. And we also have the default block. And you should remember that in an if statement, even if there is no defined else, there is always an else in the sense that there's an else branch. There's an else do nothing that always is a possibility in the code. And the same is true with the switch case. I mean, even if you do not defined a specific default block, then there's still going to be a possibility that the switch variable will not correspond to any of the case labels, and thus you'll quote-unquote fall through the switch case construct without doing anything, and that is also a branch. And the reason that I'm belaboring this point is it's very important to remember, because this point is something that a lot of people get confused about, but it is a key thing to keep in mind, because it's easy to not test certain important things by forgetting about the fact that just because there's not a if block defined or a default block defined, that doesn't mean that there's not something interesting that could happen if you hit them. Now, condition coverage. The decisions are typically made based on conditions. In pretty much every programming construct that I can think of, there's some idea of a condition that's going to evaluate either true or false, or in the case of the switch case block, there's a equivalency that's being checked, and that's a true or false check that's happening there as well. So the condition coverage says that we identify every atomic condition in the program, and we make sure that that has been evaluated once to true and once to false. Now, when I say atomic condition, what I mean by that is that if you have a compound condition, like if A greater than B and C greater than D, then both the A greater than B and the C greater than D have to be evaluated both true and false. Now, that leads us to multi-condition coverage. When you have compound conditions, not only do you want to get condition coverage possibly, but you also want to get multi-condition coverage. And multi-condition coverage is saying, I want to test every possible combination. So in condition coverage, we say, go back to the previous example, both A greater than B and C greater than D had to be both true and false. But in multi-condition coverage, we say, no, we want to test all four combinations. We want to test true, 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 false, false, true, and false, false. So that's what's happening there. You're testing all possible logical combinations. And since it's going to be defined on something that's Boolean, then it's the number of tests is going to be 2 to the power of however many atomic conditions there are. So either 4 or 8 or 16, what have you. Now, in multi-condition decision coverage, we back that down a little bit and we say, well, some of these condition combinations cannot actually affect the decision that occurs. So, for example, and we talked about if A greater than B and C greater than D, if the first condition, the A greater than B, evaluates to false, then most optimizing compilers will simply stop execution, and it will not check the second condition because it doesn't matter at that point. The overall condition has now been evaluated. It's going to be false and compound with an and. So instead of having to test 4 combinations in these situations, you would test 3. You would only test those combinations that would actually result in some evaluation of the subsequent conditions. So if you got to the point in the evaluation of conditions where any subsequent condition could not affect the decision, then you stop evaluating. And then finally we have loop coverage. Now in loop coverage, ideally you would try to cover all possible loop paths, but that's generally impossible. So usually the idea is to cover 0 loop paths, in other words, not executing the body of the loop at all. Once, in other words, executing the loop body exactly one time, once and only once, and then multiple times, and ideally that would be the maximum number of times. Now, some cases the maximum can be squishy, if you will, because the program is looping on some sort of condition that's determined by the real world, and then it can go on, for forever, basically. I mean, for example, event-driven programs, they just sit there in a basically infinite loop, waiting for events to occur until something causes them to terminate. So, how many events can Word, for example, respond to in the course of a single usage session? Well, it's not really possible to say. But in loop coverage, we would want to get a very large number of loop iterations, something that would potentially be stressful to the system. So let's take a look here. We have a simple example here, as one of you noticed at the very beginning of this presentation, is the Fibonacci program here, or a Fibonacci program. It generates a Fibonacci series using a loop. So we're going to ask first for the number of elements, and we're going to read that in, and then we're going to, if the number of elements requested is invalid, we're going to give an error message. Otherwise, we are going to print the Fibonacci series inside of a pair of curly braces, and it's going to loop around and generate the elements of the series and print them out one after the other, and then it'll exit. So in order to get statement coverage, notice that if we test with n less than 0 and n greater than 0, we will execute every one of the statements. So if we take negative 7, for example, let's go ahead and highlight this. So if we take negative 7, then we go here and we get this, and do that piece there, and then since we're less than 0, we're not going to do the body of the else, so we're going to go down here, and we're going to exit, and out we go. Now, if we then test with, say, 2, we would come in here again, and we cover this again, we get here, and then we go, okay, we're going to do the else. We come down here, and we loop around this loop a couple times, and then we exit, print out, and then we exit. So as you can see there, every statement got painted, if you will. Now, the question next here is, well, did that get us branch coverage? And there's a little bit of controversy about this, but my answer is no. My answer is that you would have to test with n equals 0 to also get branch coverage. Now, why do I say that? Well, it's because basically a loop has to be thought of as a form of a branch. It is an interesting form of a branch where it is directing the control flow back upstream as long as certain conditions are met. And then if not, it's directing the control flow around the loop body to the subsequent code if those conditions are not met. So it is a branch. It's just a branch that happens to iterate its body. And it's also, if that's not a convincing enough argument to you, for those of you who've gone through a computer science program, think about how the loop is ultimately implemented in the assembly language down at the guts of the computer. I mean, it is basically the same mechanisms by which a branch is created. There's no difference. So since what we're trying to do is test the program based on the way the program actually works, since a loop is implemented using the same constructs that are used to implement a branch, it seems to me nonsensical to argue with branch coverage doesn't apply to loops, though you will sometimes see people making that statement. Anyway, my opinion is that you would have to test with n equals 0 to not test the body of the loop once in order to get the branch coverage. Now, will this get us condition coverage, multi-condition decision coverage, multi-condition coverage? Yes, in this case it does, because there are no compound conditions. So you have to have compound conditions for there to be a difference between branch coverage and condition coverage and multi-condition coverage and so forth. Now, in terms of loop coverage, notice that we would have to test with n equal exactly 1 in order to test that. Since that's a greater than 0 value, then we could use that instead of, say, 2. And n equals some maximum. And then the maximum is going to be determined for this particular program by either a requirements specification, ideally, what's the maximum length Fibonacci series that this thing can generate, or in default of that, it will be determined by the point at which the integer values overflow. And for one of those, at some point or another, that integer variable c will overflow, and that will stop the program. Of course, it's extremely bad programming practice to rely on some sort of internal mathematical overflow error to terminate the program. So that, I would say, that is definitely a bug. So in the absence of any stated maximum, then one should test this all the way up into the point where it does overflow, and then you would file a bug against that. Okay, so let's take a look at condition coverage a little bit more closely here, just to try to clarify the point I was making a moment ago. Get my highlighter going here. So if we look at lines 1 through 5 here, these guys, if we say condition coverage, we want condition coverage, then we have to have true, false, and true and false. Right, now notice that conceivably this could be done with just 2 tests. You could have true, true, and you could have false, false, right? Which is, of course, exactly the same as what you would need for branch coverage or decision coverage here. Multi-condition coverage, then it would be, as I said before, true, 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 false, false, true, false, false. So we've got 4 tests. And then multi-condition decision coverage, it's true, 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 false, and false, don't care. They can be either true or false, so there's 3 tests. Okay, now let's look instead at lines 7 through 11, because this is an interesting possibility here. Now notice here we're checking to see if this value f is not null, and then we're checking to see what it points at. Okay, so apparently f is a pointer, and we're checking to see if the value that it's pointing at is 0. Now notice that if this first condition is false, in other words, it is null, then this second condition here is meaningless, and in fact it would be a bug to try to execute it. All right. So of course, given the way that this is defined, it should not try to execute it. Right. It should the compiler should say, okay, well that's not going to happen, and so I don't need to try that. So with this one, again, you've got true, you test true, true, and then false, but that if you test that with false, then this can't be any value one way or the other, right? Because it's nonsensical to ask what a null pointer is pointing at. So in order to get condition coverage, you'd actually have to test true and false, right? And then true, and then false, and don't care. So that would actually, in that case, multi-condition decision coverage and condition coverage would be the same thing, and multi-condition coverage would result in a meaningless test. You couldn't actually achieve it because you couldn't have false and true, or false and false for that matter, because again, this condition is undefined in the case that the pointer is null. And lastly here, let me clear this out. We look at 13 through 17, right? And now, so this is an OR. So you notice that this is the logical backward or logical opposite situation of the lines 1 through 5. So if the A less than or equal to 0 clause evaluates to true, then we don't have to go on to evaluate this because the overall compound condition will evaluate to true. So condition coverage would be the same thing. It'd be true, false, and true, false. Now, in order to check that, remember that in order to actually get this to evaluate in a compiler, you'd have to make sure that the execution flowed there, right? So this would have to be false in order for this check to happen, which is the opposite of what would happen here. This would have to be true for this check to happen. So we would have to get, we have to say false, true, and then true, false in order to get condition coverage. Now, for multi-condition coverage again will be the same as before. It's the true, 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 false, false, true, false, false. In this case, we can actually do that, which was not true up here because of this condition here. And in the case of multi-condition decision coverage, it's true and don't care, and then false, true, and false, false, the things that we need to look at there. So as you can see, that can get a little bit hairy, and just explaining it can be a little bit challenging, and then so you can imagine trying to figure it out, tracing through a program. So it's good to have tools to do this, but you do need to understand that, as I said, things like multi-condition coverage in some cases can be impossible, like in the situation in lines 7 through 11 on this slide. Okay, now, Mccabe cyclomatic complexity. This is something that you might run into if you are looking around at tools. There are tools to support this. And basically what Tom Mccabe was trying to do, and I saw that somebody sent the paper, and I'll mention the link when we go through the Q&A. You'll see this if you read his paper. Basically what Mccabe was trying to do in his research on this was to figure out why it's so hard to write programs without bugs in them. And what he stumbled on was this realization that you can look at the amount of branching in the program as a surrogate metric for its complexity. Now, by surrogate metric, what I mean is the thing that you can measure directly, which tells you a lot about something that is very difficult or perhaps impossible to measure. Now, there are many different ways that we could try to measure the complexity of the program, and some of them get pretty tough to measure, like, for example, Halstead's complexity measure, which you can find discussed in Beiser's book, Software Test Techniques. And that's a real challenge to try to get your head around what that means. Mccabe said, well, let's make this simple, that programs are complex because there's branching, where there are situations where one of two things is going to happen, or one of n things is going to happen in the case of a switch case. And since that's the situation, as you write the program, you have to keep straight in your head the possibility that there are multiple things that can happen. And that information is something that has to get stored. And psychologically, there's some work that's been done on this. And it's not just psychological, it's actually brain science. There's a part of your brain that holds the working memory, the short-term working memory, and it is very limited in its capacity. You can hold about 10 things at once at most, and then it starts to get pretty unreliable. So what that means is that if we look at the amount of branching, and if it goes well above 10, or even according to Mccabe, even above 7, then the likelihood of making a mistake goes way up. And so what this does is it looks at this metric, it looks at the amount of branching in the code, and then it says, look, if the complexity number is very high, then we would expect a higher than normal number of bugs in this particular part of the program. And for those of you who have heard of this principle before, that's the testing principle of bug clustering or defect clustering. So defect clusters are going to tend to be associated with highly complex modules, according to Mccabe's theory. Now, there is some counter literature on that. Some folks from IBM did a study on that about 4 years ago, I think it was, 4 or 5 years ago. This came out in Software Quality Professional, and you might want to look that up if you're really interested in this metric for both research done pro and con on it. But basically, that's his assertion, that programs tend to be more buggy if they're high complexity, and that certainly does make sense. Now, also, that they're harder to work on, so they're going to tend to be regression prone. So, and that also does make a lot of sense too. If you ever looked at what's sometimes referred to as spaghetti code, it's going to have very high complexity and it's very difficult to work on. Now, there's also this concept of basis paths and basis tests, and the complexity number is the same as the number of basis paths, and which is the same as the number of basis tests required to cover the control flow graph that's created when you do this analysis, at least according to the theory. Now, this gets pretty hairy here. This is for fairly complex stuff. So I'm going to show you the theoretical technique that Mccabe defined for how to calculate cyclomatic complexity, and then I'm going to tell you a couple shortcuts to that. So we take that Fibonacci program that we've been looking at so far, and we create a control graph of it. It would look as shown here. Now, in the control graph, what you've got is you've got an entry block and an exit block. And that's what you start with. You got this bubble or circle. It's called a node here. You start with an entry and an exit point, and then for every sequence of 0 or more executable statements, for example here, you draw a arrow referred to as an edge. And anytime you get to a decision point, a branch, you draw another node, this guy right here, you see. And then out of that node comes the number of decisions that can be made. Now, in the case of an if statement, there are two. In the switch case, there are as many as case blocks plus the default. So we have an edge now going out of here. This is the yes, n is less than 0. So that corresponds to this chunk of code right here. And if no, then we do the else block. So now we have this printf and these pp and stuff going here, and that's this edge here. And then now we have the loop, that guy there, I less than n. And as long as that's true, we're going to loop around here, right? So that's the body of the loop, corresponds to this thing here. And then we have this printf here at the end, which is what happens when we exit the loop. Okay, so obviously that's not a pretty picture in any way to have to draw, and this is a fairly simple program. And this drawing these things does get pretty complicated, but hang in there with me on this for a moment, and we'll get away from the graph eventually, and I'll tell you a more realistic way of doing this. Anyway, once you have the graph, you can calculate the cyclomatic complexity by looking at the number of enclosed regions. Now, enclosed region is this region here, right, because it's enclosed by the loop, and then this region here is enclosed. So number of enclosed regions plus 1, or 3, which is cyclomatic complexity. Now also, you can calculate it by taking the number of edges, which are the arrows, these guys here, and then subtracting the number of nodes, these are the bubbles here, and then adding 2. And you should get the same answer. Now, that's the hard way to calculate this. Draw the graph and then look at the regions and edges and go from there. Now, what about a somewhat easier way to do this? Now, the easier way to do this is to count the number of branching and or looping constructs and add 1. So we got an if here. That's a branching construct. You don't count the else because the else is part of the if. You got a 4. Okay, so now we're up to 2. There aren't any others, so 2 plus 1 is 3. This technique seems to work. This counting the branching and looping constructs and adding 1 seems to always work. So I would suggest that quick and dirty estimate of cyclomatic complexity, you go that way and skip drawing the graph, because obviously drawing the graph is going to get really painful as the program gets more complicated. The only complication to remember with count the branching and looping statements and add 1 is that in the case of a switch case construct, each case block counts as a 1, but the default does not. So just remember that, and then think about that for a moment, and you'll see why. Okay, let me get back to normal drawing here. Okay, now, yeah, moving on to basis paths. Let's look at the basis paths and basis tests concept that Mccabe defined, because this actually does have some utility to you. So to define the basis paths, basically what you do is you pick a path through the flow chart. So we could say we've got 1, 2, and 4 is a path, okay? And then I'm going to pick a path that's going to add one more node, 1, 2, 3, and 4. And then I'm going to pick a path that's going to add another uncovered node if there is one, or if not, then another uncovered edge. So I'm going to go 1, 2, 3, 3, 4. Basically, you're adding the minimum possible number of new edges or nodes in each of the subsequent paths, and those are what Mccabe referred to as the basis paths. Now, then what you would do, having defined the basis paths, you would then select data more or less arbitrarily that would cause the control flow to move along those paths. So a set of basis tests would be n equal 1, and n equal -1, n equals 0, and n equal 1. Now, what possible good is this to you? Well, basically, the number of tests required to get basis path coverage is about the same most of the time. I can't think of any exceptions, but it can be used as a general approximation of the number of different tests that you would need to achieve decision coverage. So if you're talking to a programmer, or you're looking at a programmer's unit tests, or if you're a programmer and you're doing unit testing and you want to just quickly check, have I gotten decision coverage, without necessarily using some sort of tool to figure that out, just look at the number of tests that you've got, as in this case, and look and quickly calculate the cyclomatic complexity using the rule of thumb that I gave you earlier, and then you're good to go. You know, if it's equal to or greater than the cyclomatic complexity, then you probably have achieved decision coverage. If not, then you probably haven't. So that's one practical application of this as well. Now there's another way to calculate the cyclomatic complexity above and beyond just that counting it up thing. And the counting will work fine if you're looking at a single function or something, but obviously if you're dealing with a file that's full of a bunch of class definitions or functions or something like that, it's going to be kind of tedious to count them. There are some tools that will help you with this. So for example, there's out on sourceforge.net, there is a free tool that will do cyclomatic complexity calculations for the Java. And I wouldn't be surprised if there's a C++ one floating around out somewhere too. So, you know, that's an option. Now, there's also Mccabe's battle map tool, which I believe is still sold. That is a somewhat bigger ticket item than a free download off of SourceForge, to say the least. Okay, so far we've been looking at control flows, so let's move on to look at data flows briefly. So what we can do to look at data flows is to use something that's called set use pair coverage. So basically what you're doing is you're looking at when a variable is assigned a value and when that value is subsequently used prior to that variable being assigned again. In other words, the value being overwritten. So what you're doing is you're watching a value flow through a sequence of variables with set use pair testing. So to go back to this Fibonacci program here, to analyze the set use pairs, what you would do is you would identify the different variables. In this case, so you've got the variables here. Let's see those guys there, I, N, P, 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 and C. And then what you have to do is you have to look at the lines where the variable is set and then where it's subsequently used. And so, for example, let's take a look at N here. We got N, we've got a set of N on 5, and then a use of N on 6. And N is only set at line 5 or line 8, right? So we set it here, and then we use it in 6. We could set it here, and if it's greater than or equal to 0, then it would be used here in the comparison. And then it would also subsequently be used here. Now, if it's less than 0, it's set and then used here, and then it's set again here and then used down here. So that's the 8 and 21. So we can then look at the values required to force the code to flow through those particular sequences that we've identified. And if we look at the values that we came up with for basis test coverage, then we can say, okay, well, what if we test with n equals 0, n equal 1, and n equal minus 1? And what you see is that you're not necessarily going to get all of the data flow coverage that you might want to get out of this set of values, because take a look at the situation where C is going to flow into P, P here, right? Value in C flows into P, and then value P flows into PP, and then it flows back into C here. So there are interesting data flows that can occur that are not necessarily going to be addressed by control flow coverage. So that's not necessarily a heartening thing to know, because I have not seen, and I'd be interested during the Q&A session if anybody has, they can certainly mention it. I have not seen any tool support for data flow coverage, at least not commonly out there. So without a tool to do that, obviously that would be tedious in the extreme. Now, Brian Merrick, in his book, The Craft of Software Testing, took a very different perspective on white box testing, and it's always good to come at the testing problem from a number of different perspectives. And so what Merrick did is he created what he called a catalog of test requirements based on his experience with things that tend to be buggy. All right, so this is kind of the original bug taxonomy-based approach to testing. It's probably the first documented instance that I can find of that. In this case, it's kind of refined, because the bug taxonomy is generalized. So you're not looking for specific bugs, but you're looking for types of bugs, and it's generalized into test requirements. And in fact, this is an interesting parallel. If you read Merrick's book and then pick up, say, James Whitaker's book, How to Break Software, or some of the subsequent books that Whitaker wrote on the same How to Break Software Security and so forth, that series, you'll see that Whitaker's concept in many ways descends from Merricks and is just a somewhat more formalized version of it, in the sense that there is a fundamental model underlying Whitaker's work of how bugs happen. But the idea that we can generalize from frequently observed bugs into things that we should test, and then we can cover those requirements, test requirements, with tests, then that's definitely very similar to Whitaker's idea. Now let me, before we look at the Fibonacci, let me go ahead and show you Whitaker's, Merrick's catalog. This is the test requirements catalog from Brian Merrick, and it is available out on his website. Not sure he sold that. It was on testing.com. It's somewhere else now. But if you were to take a look on the internet, Merrick's test requirements catalog, I'm pretty sure that you would find it, and you'd be able to see this thing. It's basically, there's a bunch of data-centric test types, as you can see here, simple data types, collections of data, pairs of data, and then it's got operations that apply to the data types. That's part 2, searching, streaming over sequences, changing contents of a collection. And so he then goes into a description of this, and we'll look at one example here. So for example, for a Boolean, you need to make sure that you've tested both the true and the false value, and if it's restricted to be 0 and 1 only, try to force it to be something else, in other words. And then different possible values that a variable can take on, and so forth. So this is a useful alternative way of looking at white box testing, is based on, as I said, where you're likely to find bugs. Let's go back to the presentation here for a moment. Now, what we're going to do is take a look at the application of Merrick's catalog to the Fibonacci program that we've been looking at here. So bear with me while I again I've got to switch applications. What I've got here is I've got the requirements, the test requirements that apply, and then the